Okay, so the next module only has two little sections. That's moments and center of mass and some more integrals with logs. The most difficult part of this module is the moments in the center of mass, okay? Just understanding the formulas and when to use them. So what we will do in this section is we will find the center of mass of objects that are on a line or a rod, something very skinny. Find the center of mass of a thin plate. So it may be, so it's kind of like, you guys know what the center of mass is. The center of mass is the place where if I were to balance something, it would balance. So if I know where that location is, then I can balance it on a point and make it so that it would be, the gravity is equally distributed in a
I have
sense
the
to
information
the
for you.
mass. What'd you say?
I'm trying to find, oh, sorry. I'm trying to like look for center of mass information. I'm sorry. I was trying to do something.
Okay. So I'm going to give you the center of mass equations. I'm not going to just let you hang here. I'm going to give them to you. Okay. All right. Locate the center of mass of a thin plate. Use symmetry to help locate the centroid of a thin plate and apply the theorem of Pappus. Okay. So what does a mass along a line look like? All right. So I always like this example because it's the one that I think anybody can relate to, unless, I mean, I know back in the 60s. Whoo, that sounds a long time ago, doesn't it? I was born in the 60s. So back in the 60s, our parents would take us to the playground and there would be, what you call this thing, a seesaw. Okay. And so it would have some post right here on the ground like this. And then you and your friends would come and pop on the end of the seesaw and make it go up and down, up and down, up and down. Now, clearly, if both of you weigh about the same weight, you're going to have a fantastic seesaw experience. When one goes up, the other one comes down, one goes up, the other one comes up, and blah, blah, blah. So you're doing it like this. If your friend is a whole lot bigger than you, then neither one of you are really going to have a great seesaw experience if you sit in the same location, because the heavier person is going to want to make the seesaw go down, and then the light person will be stuck in the air. How can you fix that? Well, there is a way to fix that. If you move the heavier person out further in the seesaw, then you can have a wonderful seesaw experience. Okay, so this is going to be 0. And I'm going to put a mass right here, M1, at location X1. I'm going to put another mass right here, M2, at location X2. And I'll put another mass right here, M3, at location X3. Okay, so based on this mass, these three masses, they're going to want to rotate based on how far they are and how heavy they are. Okay, so first off, we know that the force of any given mass is its mass times acceleration. So it's the mass in kilograms times the acceleration in, that's the force due to gravity. So this mass has a force, F1, equal to its mass times gravity. This one has a force, F2, equal to its mass times the gravity. And this last one over here has a force, F3, which is equal to its mass, again, times gravity. So this one, when we rotate this direction, this is what we call negative torque. Okay, that's in clockwise direction. And uh-oh, something wrong here. Over here is positive torque. Okay. All right, so each force wants to turn the axis about the origin. Okay, it wants to be able to rotate like this. Okay, so the torque is the turning effect. Yes, that is right. Well, it was spelled with A. So it is based on plus or minus, all right, the mass, the force times the gravity times its location relative to the origin. So x1 would be a negative location. X2 and x3 would be positive locations. Okay, so now I can talk about the system torque. So we're going to add all these up. So this is going to be the sum, I equals 1, in this case, n. Our n is 3. So let me just put it there, 3. And I'm going to add them all up of mi g times xi. So this will be m1 g x1 plus m2 g x2 plus m3 g x3. All right, so I can pull the g out and I get the sum I equals 1 to 3. And the only thing that's left is the mi xi. So that's g times m1 x1 plus m2 x2 plus m3 x3. Okay, so this part right here is the moment about the origin. Okay, so therefore, we can then define the moment about the axis, which for us is, that should say origin. We're going to call m naught. It is the sum I equals 1 to n of all the masses times their distance from the origin. And the xi is, if it's negative, if it's on the left side, it's negative. If it's on the right side, it's positive. So that counts. Okay. I'm not there yet. Okay, so our goal would be to place the fulcrum Dr. Lott, what's the fulcrum? This thing is the fulcrum. So our goal would be to place the fulcrum at a location that balances the system. Okay, so we have this thing. All right, we have these masses. So I have this mass, M1, here's X1. Okay, here's the origin. All right, did I have an origin on the other one? I did not have an origin. Oh, yes, I did. The origin was there because I assumed that one was balanced. Okay, so here's the origin. Maybe the fulcrum needs to go there. Here's X2, M2, X2. And here's M3, X3. So what we're going to learn on Monday is how to figure out what this is. This point right here is going to be the center of mass. That is the place that balances the system. Okay, I will have office hours tomorrow. No physical therapy tomorrow, so I have office hours. I will see you then. Have a great weekend.